So when we talk about swarm robotics, we are talking about some specific properties that I'll just highlight. Now, number one is that the number of robots in a swarm, and let's say there are thousands in number, more than thousands in number. So I'm not talking about one robot, I'm talking about two robots, I'm not talking about three robots. I'm talking about the same number of robots as there are ants in your food, as there are bacteria that they attack and pain you. I'm talking about the same number of robots as there are coronavirus insects, virus in the world as of now. I'm talking about the same number of robots as they are in any migration of birds. So birds migrate in humongous numbers. So I'm talking about thousands of robots. So let's be very clear on that. And because there are thousands of robots, I will soon get into algorithms. So my algorithms have to be completely decentralized in nature. So there are two types of algorithms. Decentralized algorithm where one robot says, I'm the leader, I'll collect all your information, I will decide what each one of you should do, and you have to do exactly what I say. So every robot gives the leader all the data, the leader does this mastermind planning, this person this duty, this person that duty, this person does this, these two people do this, and then it tells all the robots, you take the, you do this, you do this, you do this, you do this. It's not possible with thousands of robots. So there are too many robots. So 1,000 people giving their data to this one robot, and imagine the kind of data to be processed, and imagine that your decisions are being made or corrected or being adapted for uncertainties at the rate of 100 hertz. So you need to make 100 decisions per unit. You need to make 100 decisions every second, and one decision will involve thousands of robots giving their data, a robot processing all that data and giving the results back. It's not going to happen in a centralized system. So decentralized, we say every robot makes its own decision. Nobody's a leader. And you see that. So, I mean, this institute is actually a mix between centralized and decentralized, but seen from a global level, it's centralized. So, we all report to the director makes decisions and tells us what to do. Of course, at the micro level, we are decentralized. Like, director did not write the script of this lecture, neither did I. So, decentralized systems, that means every robot makes its own decision without any leader. So there's no leader who decides for all the robots. Now, because it's decentralized, we'll have to put one more constraint, and because we'll have to do one more we'll have to do one more constraint, and that constraint is that the robots only have local sensing. So every robot can only look at only the things which are around itself, and that's again important because, same example, if one robot is making its decision based on the observations of thousands of robots and it's working at 100 hertz, the amount of data with that one robot is too much. Now, local sensing is now better understood because obstacle avoidance, only the nearby obstacle mattered to us. Far away had the potential zero, vector field histogram were pruned out, velocity obstacle were pruned out. So we anyways know that reactive visions are all local. They may not be optimal, but they are local, they are fast. So every robot will only sees the few robots around. Now, we're talking, of course, we talked about multi-agent systems, and this is also a multi-agent system where the number of agents are thousands. So we said that we will classify them based on communication, and if based on communication they have a communication, then I say they can only have local communication. So the robots can, using formal tools, communicate to each other, but then this communication should only be local. You cannot contact a robot which is very far away because you don't need to. And that's exactly the same as local sensing. So using all your physical sensors, cameras, or sensors I'll talk about, you can only look at the robots around, and the same is with communication as well. You can only talk to the local robots around. So every robot only communicates, and because I've used sensing over here, so let me clarify, using formal communication channels with the local robots. So that's almost the same property. So let's go on to why did we apply all these constraints? Because my algorithms are going to be reactive in nature. Now, the reactive algorithms are the ones where the complexity is. So the reactive algorithms are the one where the complexity is 1. And it's obvious because I've restricted what information goes to the algorithm to small numbers. So now you've got limited information. So now you can only do some quick arithmetic potential field and just calculate your V omega. So it's obviously reactive. And of course, from the introduction, a simulation of swarm, which I'm not sure why should you be doing, because now I'm talking about physical real robots, will be n log n, where n is because you ultimately need to simulate n agents. There may be n agents, but n real agent, n simulated agents, your computer will have to have n parallel threads, and log n for the proximity queries. So that's the proximity, that's a constraint of the proximity queries. So the sensors are good in this regard. The sensors will only see around, but then in a computer program, the sensors need to be simulated, and the simulation of the sensors needs proximity queries. So this is because of the proximity queries. Okay, so interesting enough, there's a related term that the algorithms also have to be distributed. Decentralized is from the algorithm perspective that every robot makes its own distribution, makes its own decision. So distributed is more from an application perspective. So all robots divide the work among themselves. So if I ask a swarm of robots to clean a room, it's not that one robot is cleaning and the others are just enjoying. Not like group assignments, one person is doing the entire assignments, the others are enjoying. Every robot needs to do its bit, and because there are thousands of robots, every robot in fact only does a bit, and the cleaning will happen because thousands of robots are doing it in parallel. So every robot only does its bit and everything happens this thing. Now, the moment we talk about all these things, natural swarms and everything, a popular question comes is, what really makes the human brain that powerful, and why couldn't we make an artificial brain? Not going into those debates, but the answer comes out to be the parallelism. So in brain, of course, the neurons are slower than what modern day processors can do, but then all the neurons are their own processors. So when we say 10 to the power of 11 neurons, all of them are working in parallel as physical units. So thousands of robots, they're all working in parallel. If you go to simulation in a laptop like the one that I'm using currently, there's only one processor which is simulating all of them up. So it's not really parallel. Now, when you're talking about swarm, we are talking about highly parallel systems. So every robot is physically independent and it has its own processor, and its own little processor is doing whatever you're asking it to do. So it's extremely, extremely parallel. So imagine that a swarm of 1,000 robots, you imagine as 1,000 parallel processors, or swarm of 10,000 robots as 10,000 parallel processors. That will almost make the cluster computing center that we have, and that's also what physically happens. Now, if you see one ant, the brain is too less, but then how many ants are there? Probably infinite. And because I've put this constraints of 1,000, so the obvious constraint will be, in robotics people talk a lot about cost. The modern day robots cost like 30 lakhs, 50 lakhs, 2 crores. 1,000 times 2 crores, even the government will not be able to purchase it up. So we have extremely low cost as a constraint. So these robots should be like just chips with all the sensors, miniature versions of that, and with little actuators. So 100, 200, 500, those are the kind of costs, and not the crores which modern day robots have. So extremely low cost. And that's what will drive my choice of hardware, because if any hardware, LiDAR is 1 lakh, I need robots which are less than 1,000, so it's not possible to get a LiDAR. And because it's not possible to get a LiDAR, I absolutely cannot afford it. And because I cannot afford it, I will not use those kind of hardware. Let's quickly go into the others. So because they are low cost, and the thing that naturally happens that they are scalable, that means I can just increase robots on the fly from 1 to 10, 10 to 100, 100 to 1,000, thousands to 10,000s. I can just increase robots and the algorithms will still behave, which is not most of the programs that you write, and scalability is a major concern. So when you test it on your systems, all those searches that you make, all the sorts that you make, those naive insertion sorts, you test it with 100, 200 numbers, they work well. I use an automated script to judge that, and with my inputs it doesn't work. The size of the data changes. You test it for a few hundred, for 100. I'll test it for maybe 100,000. So then we start talking about scalability, and scalability is absolutely very important for Swarm, because I could just increase robots on the fly like anything, and because the complexity is strictly O of 1 in terms of the real robot, it doesn't matter how many robots I add, and it's not O of 1 of simulation, it's O of 1 of real robots which are working in parallel. So I can just add the robots will still behave perfectly well. So it's extremely scalable. Now there are two caveats that are sometimes placed. One is homogeneous. We talk about a flock of birds, all of them are birds, with the same, broadly speaking, with the same kind of organs. Some may have a better eyesight, some may have a better good looks, but they're all birds. Ants, they're all ants with more or less the same organs. In fact, with the same organs, some of them may be more efficient in something. So we talk about homogeneous swarms. I say it with a caveat because, of course, in research, a lot of work has happened where there are two kinds of swarms, or there are three kinds of swarms that interact with each other. So if you say they are, I mean, it's a swarm of three different types of agents, then they are not homogeneous. Homogeneous is still a correct thing to say because it's not one swarm, it's three swarms. The best example is I use some aerial swarm robots to give an inspection of the entire area, but then the aerial robots cannot really correct what is the problem on the ground. People have thrown a lot of litter, and that needs to be clean. Aerial robots are not going to do, and therefore you have got the second type of swarms, which is the ground robots, which will go around and just pick up the litter and just throw it on its where it should be. But then again, the ground robots only need to move a little bit, and the dustbin will be very small, so you don't need the ground robots to really travel a mile or so to put it into the dustbin and then come back again. So you've got the third type of swarm, which make it more or less like a conveyor belt system. So they take things from the ground robot, they go and they offload it up, they come back. So the utility of three types of swarms are all different. One can see well, the other can pick well and travel. I mean, it has those nice clippers and manipulators, and the other one is good for transport. So three different types of swarms, non-homogeneous as an entire system, but then if you talk about each and individual swarms, they are homogeneous. All aerial swarm robots are the same, all ground robots are the same, and all transportation robots are exactly the same, and that's why sometimes you also say it has to be flexible. So I need robots to clean litter one time, they should be able to do that. But then I also want my robots to guide a human where to go. The same aerial robot should be able to provide the vision. I want them to make characteristic shapes because there's a visitor who's coming to the laboratory, they should be able to dance. So the same swarm should have multiple users. And because the same swarm should have multiple users, therefore, my hardware should remain the same, and just by changing the controller at all of them through a script, that's flexible electronics, not going into the electronics components. Remember that they are not real big robots that will have an Intel processor inside them, that will also have a hard disk and RAM inside them, which is big robot, which has a full computer system inside it. You can write down whatever program. These are electronic circuits only at the hardware level. So the electronics needs to be programmable so that I can reprogram them for a different task based on need. And that's why it makes it different from a multi-robot system. So a multi-robot system does not really have these properties. So a multi-robot system, you typically deal with, I mean, I think the maximum multi-robot system that I have simulated is 10. Beyond that, it was, I mean, I've done a lot of simulation on swarms. We've got excellent centralized algorithms as well, although in multi-robot systems also, the centralized solutions are only used when they are less than 5 robots. For 5 to 10, we obviously go for decentralized. There's a reason why we only take in probably 10 robots, because if one of the robot is gonna be expensive, like lakhs, 10 robots is like crores, and I don't have money to do that. Of course, I don't even have money to buy a single robot, but then limited funding is given by the government. So multi-robot systems could be both centralized and decentralized, sometimes a mixture of both. The multi-robot system use a lot of global information as well for different kinds of things, and they also use a lot of global information for different kinds of things as well. Like based on global information, they could actually decide that this route from which I am going is gonna have problems pretty soon, so let's take something else. Or based on global information, it could again find out that yes, there is a lot of congestion and I should avoid that up. They could be deliberative and reactive as well. We looked at it. They could be a mixture of deliberative and reactive. We looked at it. So, multi-robot systems are typically for different applications and the robots interact with each other. So, there's no question of them being completely distributed as well. Physically, they are parallel as well, but it's not that it's thousands of threads in parallel. So each one of the robot could have its own thread, which does a lot of computation as well. They are extremely expensive. I hate robotics field for that. We're not the richest country in the world. We cannot afford a lot of robots, and of course the algorithms are not scalable. So I've done a lot of publications on multi-robot system. You actually have to code till how many robots have you tried, and that's why the numbers become absolutely very important.